Hey team, I'm Maddie. Welcome to ScienceSideUp, and today we're going to talk about how the Galapagos Islands formed. So last summer I had this absolutely amazing once-in-a-lifetime opportunity to go sail around the Galapagos Islands for a week, and it was one of the greatest experiences of my life. I wanted to do a video or two or 12,000 on the Galapagos Islands. I bet you think I'm going to start talking about Darwin's finches and all of the amazing wildlife that's on the Galapagos, and those are certainly really cool topics, but that's like biology and squishy science and not what I like. But just to satisfy everyone, here's a finch. Here's another finch. And here's a swimming iguana. Now let's talk about rocks. To me, what makes the Galapagos Islands just really cool from a geology standpoint is the location of the Galapagos on the Nazca tectonic plate. So the Nazca plate is doing some interesting things. Notice that it's moving away, so it's trying to move southward from the Cocos plate above it, and at the same time it's moving towards the South American plate. So it's not, the Nazca plate is moving in a complex manner, which means that the Galapagos Islands formed in kind of a clump instead of a nice line like, say, the Hawaiian Islands. And then just another cool thing about the Nazca plate is where it's diving under the South American plate in that subduction zone. That's actually helping to build up the Andes Mountains, which I think is pretty cool. So let's start with some Geology 101. We, as humans, we live up on the top of the Earth's surface, which is the Earth's crust. And below the crust is the mantle. And the boundary that separates the crust from the mantle is called the moho. The moho's proper title is the Mohorovici discontinuity. I am really sorry if I butchered that name. It's named after who discovered it, who was a Croatian seismologist whose last name was Mohorovici, or however you're supposed to pronounce that. But geologists generally abbreviate it as just the moho. So we've got the crust, the mantle, and the moho. Every once in a while in the mantle, you'll have something called a hotspot. So that's a region in the mantle that is hotter than the area around it. Now, a common misconception is that the mantle is a liquid. That's not true. The mantle is in fact a solid. We know that from seismic waves. You can check out my video on, it's called Journey to the Center of the Earth, but it's how do we know what the interior of the Earth looks like. So the mantle is a solid. And if we want to make crust, right? If we want to make an island or make a continent or anything like that, we have to melt some of the mantle and bring it up through the moho to the crust, and we'll start forming new crust. So one of the ways to do that is when you have one of these hotspots, and for now let's just accept that those exist at certain places and not concern ourselves with why they exist where. So we have places that are warm in the mantle, and that warming causes melting of the rock, right? So over time, this is going to start to push through the crust, push through the moho and start to form crust. So let's see, I've got a brownish color, so maybe we'll make a little mound, and then it'll come again, and we'll make some more. And this is a volcano. That's what we've got going on. So that's basically what's going on in this video. except that you've got to imagine that red fizzy stuff freezing as it comes out of the volcano. Now, for a volcanic island to form, we're going to think about this being all happening underwater. So there's our ocean surface. I'm going to draw a happy little fish. That's a fish. Here's another fish. Cool, happy little fish. So as time goes on, this volcano erupts and more material builds up. Until it breaches the ocean surface, and now we've got an island. Now this process takes tens to hundreds of thousands of years of just, and it's not continuous. It's one volcanic eruption, and then a while later, another volcanic eruption, and then a while later, another volcanic eruption. So this is happening over geologic timescales. When I say geologic timescales, really long periods of time. Again, tens to hundreds of thousands of years. So over that time, this guy, this green line we've got here, let's consider that to be our tectonic plate. Well, this whole plate can move. When the whole plate moves, we're going to move the crust, but not the mantle. So now our hotspot that was here, right? If we move this guy over, now that hotspot is going to be over here. So the way I just drew it, it looked like the hotspot moved, but I didn't want to erase my whole drawing and start over. That's not what happened, right? The crust moved over the top. And so now the hotspot is here relative to the old island, and we can start to make a new island, again, over a time span of tens to hundreds of thousands of years. And this process just keeps going as long as that hotspot exists. Now, when I was in the Galapagos, one of the things I was lucky enough to see was a fairly recent lava field. By recent, I mean the volcano went off and erupted in the 1800s. But here are some really cool pictures from this young, geologically young island. So this is classic ropey lava. What happens is that as the lava is flowing, it comes against something in its way, and it pauses in its flow and it cools. And then the lava that's flowing behind it comes up against that lava that started to cool and solidify, and then it itself starts to cool and solidify, and so on and so forth, forming a series of ridges and valleys. Here's another great example of that ropey lava, but it's twisting on itself and looks really cool. And as you can see, like, these ropes are thicker than the ropes in the previous picture. So this was probably a slower flowing lava. And this one would be even slower flowing. You can still see some of that ropey structure. But I don't know, I look at this image and I think it's just beautiful because you can just kind of see, think of it as like molasses sliding down a hill but freezing in place. So you can really see the movement of the lava. Now this formation's a little different. You can almost see where it's trying to be that ropey shape, but then there's just these holes, right? So what's happening is that while the lava that's on the surface in contact with the air is solidifying, the lava that's just immediately below it is so hot that it bursts through the surface and just keeps flowing. Here's some examples of that on like a larger scale. These formations are sometimes called ovens. So what's going on is that the lava is building up vertically, building up, building up, building up, but then the outer shell cools until the inner part just bursts through. You can see that really strong crack in this image, and then even like layers of lava coming down on the outside. Here's another example of that. I think this is just the most beautiful thing. These lava ovens, and they're completely hollow inside. Here's 3 all together. Now, when that process happens horizontally instead of vertically, you get formations called lava tubes, which is what you're looking at here. Lava tubes can form underwater or on the surface, but all of the pictures I have here are underwater. So you have that lava that's flowing, and the outside of it hardens and solidifies, while the inside is still hot and liquid, and it keeps moving. Until now that's the outside and it solidifies. That is me snorkeling, and I had so much fun exploring the lava tubes this way, and I was delightfully interrupted by this little guy. So the rest of my pictures are of this penguin who decided he needed to come swimming with me. So anyway, that's all I've got for you guys today. I hope you enjoyed this video. Remember to like and subscribe if you haven't already subscribed to the channel, and I will see you all next time. Bye, team.